Ever since we first gazed up at the stars, humanity has been driven by an unshakable curiosity, a deep, intrinsic need to understand what lies beyond our world. That longing has carried us from ancient myths and celestial legends to the very edge of interstellar space. We are explorers by nature, dreamers by design, and today we stand at the threshold of a new era, one where the mysteries of the cosmos are no longer out of reach. We've walked on the moon, sent probes to distant planets, and built telescopes that peer back in time. But what comes next may redefine not only science, but our very existence. Some missions are more than just missions. They hold the potential to reshape our understanding of life, the universe, and our place within it. Imagine discovering life on another world, or unraveling the secrets of dark matter, or finding a new home among the stars. These aren't scenes from science fiction. They're the ambitious goals of real space missions happening right now, missions that could alter the course of human history. They promise answers to questions we've asked for millennia and solutions to challenges we face here on Earth, from climate change to resource scarcity. This is about more than rockets and data. It's about hope, wonder, and the next great leap for humankind. So today, we're embarking on a journey through 25 space missions that could change everything. From ventures that will touch the icy moons of Jupiter to telescopes that will map the infancy of the universe, each one represents a bold step into the unknown. You're about to witness missions that hunt for alien oceans, probe the nature of black holes, and maybe, just maybe, find another Earth. This is where science meets imagination and where humanity's greatest ambitions take flight. So settle in, open your mind to the possibilities, and get ready to explore the missions that aren't just reaching for the stars, they're reaching for forever. Our journey begins not with a distant probe or a rover on an alien world, but with an observatory that has already fundamentally rewritten the rules of modern astronomy. Floating 1,000,000 miles from Earth, the James Webb Space Telescope is humanity's most powerful time machine. It doesn't travel through years or decades. It peers across billions of them, capturing light that has been traveling since the very infancy of the cosmos. Every image it sends back is a postcard from the past, offering us a front-row seat to the formation of the very first stars and galaxies that ever flickered into existence. This isn't just an upgrade from its predecessor, Hubble. It's a complete paradigm shift designed to see what Hubble never could. While Hubble showed us the visible universe in stunning detail, Webb is built to see in infrared light. This is the key to its incredible power. The expansion of the universe stretches the light from the most ancient objects, shifting it from the visible spectrum into the infrared. To our eyes, that early light is invisible, but to Webb's golden hexagonal mirrors, it's a clear and brilliant signal. It's like discovering we had been listening to the universe's story with our hands over our ears, and Webb has finally allowed us to hear the faint, whispering opening chapters. And what it's hearing is already turning science on its head. Cosmological models predicted that the first galaxies would be small, simple, and slowly evolving. But Webb is finding massive, fully formed galaxies earlier in the universe's timeline than anyone thought possible. It's as if we opened a history book expecting to find the first simple sentences, but instead discovered complex epic poems written on the very first page. These discoveries aren't just curiosities. They are forcing scientists to reconsider the fundamental processes of galaxy formation and perhaps even the very timeline of the universe itself. But its revolutionary work doesn't stop at the dawn of time. Webb is also our most promising tool in the search for life beyond Earth. By staring at distant exoplanets as they pass in front of their host stars, it can analyze the starlight filtering through their atmospheres. Within that light are chemical fingerprints, biosignatures like oxygen, methane, and carbon dioxide that could indicate a world isn't just habitable but actually inhabited. It's the first telescope capable of sniffing out the air on another world light years away, bringing us closer than ever to answering the profound question, are we alone? While Webb looks to the cosmos, a new program is turning our attention back to a world we once visited, but never truly conquered. The Artemis program is not a simple rerun of the Apollo era. It is a fundamental reimagining of our relationship with the Moon. Apollo was a series of brilliant, short visits, flags, and footprints on a distant shore. Artemis, named for the twin sister of Apollo, is about building a home. Its goal is to land the first woman and the first person of color on the lunar surface by 2025, not as a finale but as a foundation. This time we're going to stay. The architecture supporting this ambition is a symphony of next-generation engineering. At its heart is the Colossal Space Launch System, or SLS, the most powerful rocket ever built. It's designed to be the workhorse, capable of hurling the Orion spacecraft and its crew beyond Earth's grasp with raw, unprecedented power. Orion itself is a technological marvel, a capsule built for deep space, offering more living space than its Apollo predecessor and advanced systems to keep astronauts safe on their week-long journey to the Moon. But the real genius of Artemis lies in its modular, sustainable approach centered around the Lunar Gateway. Imagine a small space station, not in orbit around Earth, but around the Moon. The Gateway will serve as a multi-purpose outpost, a science lab, a short-term habitation module, and most importantly, a staging point for descents to the lunar surface. Instead of a single, massive ship making the entire journey from Earth to the Moon and back, astronauts will transfer from Orion to a human landing system docked at the Gateway. From there, they can make the short trip down to the surface, return to the Gateway to resupply, and then catch an Orion capsule back home. This hub-and-spoke model is the key to a permanent presence, turning the Moon from a destination into a neighborhood. The scientific and technological payoff of learning to live and work on the Moon is immense. We will learn how to utilize local resources, a concept called in situ resource utilization. This means learning to extract water from permanently shadowed craters at the lunar pole's water that can be drunk, used for radiation shielding, or split into hydrogen and oxygen to create rocket fuel. Mastering this process is absolutely critical for the next, even greater leap, sending humans to Mars. A trip to the Red Planet would be a multi-year mission, impossible without the ability to refuel and resupply along the way. The Moon is our proving ground, a nearby workshop where we can perfect the survival skills we will need to become an interplanetary species. Perhaps most inspiring is the collaborative spirit driving Artemis forward. This is not a solely American endeavor. NASA has established the Artemis Accords, a set of principles for peaceful and cooperative space exploration, and international partners from Europe, Japan, Canada, and beyond are contributing crucial components. The European Service Module provides Orion with power and propulsion. Canada is building a sophisticated robotic arm for the Gateway, and JAXA, the Japanese Space Agency, will contribute critical habitat elements. This global effort mirrors the cooperation seen on the International Space Station, proving that humanity's greatest explorations can be a unifying force, building bridges between nations even as we reach for another world. Artemis is more than a mission. It's the beginning of a new chapter in our story, one we are writing together. While Artemis lays the groundwork for a sustained human presence on the Moon, another mission is undertaking a task so complex it has never been attempted anywhere beyond Earth. The Mars Sample Return Campaign is arguably one of the most ambitious robotic space endeavors ever conceived, a multi-mission, multi-agency cosmic relay race with the ultimate prize, bringing a piece of another world back to our own. This isn't about remote analysis or sending data back through space. It's about holding tangible evidence of Mars in our hands, allowing our most powerful laboratories to scrutinize it for answers to questions that have haunted us for centuries. The first runner in this incredible relay is already on the ground and hard at work, NASA Perseverance rover. Since landing in Jezero crater in 2021, this robotic geologist has been meticulously exploring what was once a river delta, a site scientists believe is one of the most promising places to find evidence of ancient microbial life. Perseverance isn't just observing, it's collecting. Using a sophisticated drill system on its robotic arm, it has been coring samples of Martian rock and soil, sealing each one in an ultra-clean titanium tube and depositing them in a carefully documented cache on the surface. These tubes are the treasure, and Perseverance is building the map to find them. But the real engineering marvel lies in the next steps. The plan requires a second lander to travel to Mars, touching down perilously close to the sample cache. This lander will carry two unprecedented pieces of technology. The first is a small fetch rover provided by the European Space Agency, which will scurry out, locate the sample tubes, and bring them back to the lander. The second, and perhaps the most audacious component, is the Mars Ascent Vehicle. This will be the first rocket ever launched from the surface of another planet. The fetched samples will be loaded into a container about the size of a basketball, which the Mars Ascent Vehicle will then blast into Martian orbit. Waiting in that orbit will be the final player in this interplanetary handoff, the Earth Return Orbiter, also built by ESA. This spacecraft must locate and rendezvous with the orbiting sample container, capture it, and then hermetically seal it within a robust biocontainment system to ensure absolutely nothing from Mars contaminates Earth's biosphere. Only then will it begin the long journey home, eventually releasing the Earth entry capsule for a dramatic parachute-assisted landing in the Utah desert, where a team will be waiting to transport the priceless cargo to a state-of-the-art, secure facility for analysis. The scientific value of these pristine samples cannot be overstated. Our rovers are incredible, but they are limited by the instruments they can carry. On Earth, we can subject these samples to the full might of human scientific inquiry, powerful electron microscopes, mass spectrometers, and sequencing technologies that can detect organic compounds and potential biosignatures at a scale far beyond anything possible on Mars. This could provide the first definitive evidence that life once existed elsewhere in the universe. Beyond the search for life, these rocks hold a detailed record of Mars's geological and climatic history, offering clues to why a world once warm and wet became the cold, arid desert it is today. Understanding this planetary evolution is not just about Mars. It's a mirror we can hold up to our own planet, helping us comprehend the delicate factors that allow a world to sustain life. This mission is a gamble of epic proportions, but the potential reward is a revolution in our understanding of biology, geology, and our place in the cosmos. Leaving the red sands of Mars behind, we now journey to the outer solar system, to a world that is nothing like our own, yet may hold the keys to one of our most profound questions. Orbiting the giant planet Jupiter is Europa, a cracked and icy moon that has captivated scientists for decades. Its surface is a labyrinth of deep ridges and frozen plains, but it's what lies beneath that has sparked one of the most exciting hunts for life in our cosmic neighborhood. Hidden under an ice shell estimated to be miles thick is a global liquid water ocean, containing more than twice the volume of all Earth's oceans combined. This isn't a cold, still sea. Evidence suggests it is kept warm and liquid by the immense gravitational forces of Jupiter, which flex and heat Europa's interior through a process called tidal heating. This combination of liquid water, essential chemistry, and a lasting energy source checks all the boxes for a potentially habitable environment. To explore this distant, enigmatic world, NASA is building one of its most sophisticated interplanetary explorers ever, the Europa Clipper. This isn't a lander or an orbiter in the traditional sense. Jupiter's radiation belt is an incredibly harsh environment, bathing anything that gets too close in particles that can fry electronics. Instead of orbiting Europa directly and succumbing to that radiation, Clipper is designed for a brilliant, dance-like mission. It will orbit Jupiter itself but perform a series of nearly 50 close flybys of Europa, swooping in to gather a torrent of data before retreating to the slightly safer depths of space. Each pass will be like a high-speed reconnaissance run, building up a complete picture of the Moon piece by piece over several years. The suite of instruments onboard Clipper reads like a scientist's dream wish list, each one designed to probe a different secret of this icy world. A powerful ice-penetrating radar will fire signals down toward the surface, measuring the thickness of the icy shell and hunting for pockets of liquid water that might be much closer to the surface, trapped within the ice itself. This could reveal potential access points between the surface and the ocean below. A thermal instrument will scan the frozen surface for recent eruptions of warmer water, while a high-resolution camera will map the complex terrain in stunning detail, searching for geological evidence of that subsurface ocean interacting with the surface. Perhaps most crucially, other instruments will work to literally taste the Moon. A sophisticated mass spectrometer will analyze the composition of Europa's incredibly thin atmosphere, and during its lowest flybys may even fly through plumes of water vapor that are thought to erupt from the ocean below like geysers shooting into space. If Clipper can directly sample the material from that hidden ocean, it could detect organic molecules, the building blocks of life. Another instrument will use ultraviolet light to hunt for these plumes and analyze their composition. Together, these tools will allow us to understand the chemistry of Europa's ocean, its salinity, its acidity, and whether it contains the necessary ingredients to support living organisms. The ultimate goal of the Europa Clipper mission is not to find life itself, but to definitively answer whether this distant ocean world has all the conditions necessary for life as we know it to arise and survive. It is about understanding the habitability of this alien sea. The implications of a positive answer would be nothing short of revolutionary. It would prove that the recipe for life is not unique to Earth and that habitable environments can exist in the cold, dark depths of space, powered by the gravitational tug of a giant planet. This would fundamentally shift our perspective on where we might find life, not just in our own solar system, but around the countless moons orbiting gas giants in other star systems. Europa Clipper is our first dedicated voyage to an alien ocean, a mission that could transform a moon of ice from a point of light in a telescope into a world of breathtaking potential. But if Europa represents a hidden ocean, our next destination offers a world that is almost shockingly familiar, yet utterly alien. We travel now to the largest moon of Saturn, a place unlike any other in our solar system, Titan. This is not a barren rock or a simple ball of ice. Titan is a world shrouded in a thick, hazy atmosphere, with rivers carving valleys into its surface, great lakes pooling in its polar regions, and even seasonal rain. But these aren't made of water. On the frigid surface of Titan, where temperatures hover around -290 degrees Fahrenheit, the role of water is played by liquid methane and ethane. It is a world with a complete hydrological cycle, just with a completely different chemistry. This bizarre, Earth-like landscape makes Titan a prime candidate in the search for life, or at the very least the building blocks of life. To navigate this unique and complex environment, NASA is developing a mission that is as revolutionary as its target. Dragonfly is not a rover that will crawl slowly across the surface. It is a nuclear-powered, car-sized dual quadcopter, essentially a large, sophisticated drone designed to fly through Titan's dense atmosphere. The air on Titan is about 4 times thicker than Earth's, and the gravity is only 1/7 of ours, making it an ideal world for flight. A rotorcraft can cover more ground in a single hop than a rover could in years, transforming our ability to explore this distant moon. Dragonfly's mission is one of profound astrobiological significance. It will explore multiple, vastly different environments across Titan's surface, from the vast, dark dunes of organic sand to the floor of an ancient impact crater where liquid water likely once mixed with complex organic material. The science hinges on the fact that Titan is a colossal factory of probiotic chemistry. Its atmosphere, rich in nitrogen and methane, is constantly being broken apart by sunlight, leading to the creation of ever more complex organic molecules. These molecules then drift down like snow, coating the surface and potentially undergoing further reactions in the liquid methane lakes. This process is thought to closely mimic the conditions on early Earth before life emerged. Titan is essentially a frozen, albeit active, laboratory preserving the steps of chemistry that may have led to life on our own planet. The drone will land initially among the dunes to sample these organic sands, then make a series of daring flights, each one carrying it several miles to a new location, ultimately reaching the Selk impact crater. There, it will look for evidence of past liquid water and complex molecules that have interacted with that water. Its entire body is a suite of scientific instruments capable of drilling into the surface to feed samples into a mass spectrometer that will identify the complex chemical soups present. It will study the moon's geology and atmosphere and even listen for seismic activity. Understanding what Dragonfly finds could fundamentally alter our definition of habitable zones. Life as we know it requires liquid water, but Titan forces us to ask a different question. Could a different kind of life, with a biochemistry based on liquid methane instead of water, exist in such an environment? Even if it doesn't find signs of such exotic life, the mission will provide an unprecedented look at the chemistry that precedes it. Dragonfly is not just exploring a moon, it is conducting an archaeological dig into the chemical pathways of life itself, offering us a glimpse back in time to our own planet's earliest days and expanding our imagination for where and how life could take hold in the universe. While the James Webb Space Telescope acts as a powerful zoom lens, focusing intensely on specific cosmic targets with incredible detail, its successor is being built with a radically different and equally powerful vision. The Nancy Grace Roman Space Telescope, named for NASA, a first chief astronomer who is often called the Mother of Hubble, is designed to be a wide-angle lens for the universe. Its primary mission isn't to stare deeply at one spot, but to sweep across vast stretches of the sky with a field of view 100 times larger than Hubble's infrared instrument. This extraordinary capability will allow Roman to perform the first wide-field, high-resolution surveys in infrared light, creating an unprecedented cosmic map that will tackle some of the most profound mysteries in modern physics. The most pressing of these mysteries is the nature of dark energy, the unknown force causing the expansion of our universe to accelerate. We know this force exists and dominates the cosmos, making up about 68% of all the energy in the universe, yet we have no idea what it actually is. Roman is specifically designed to measure its effects with more precision than ever before. It will do this through three powerful techniques, creating a multi-pronged attack on the problem. First, it will observe thousands of distant supernovae, using these exploding stars as standard candles to measure cosmic distances and track how the expansion rate has changed over billions of years. Second, it will map the distribution of millions of galaxies, studying the large-scale structure of the universe to see how dark energy has influenced the growth of cosmic structure. Finally, it will measure the subtle distortions in the light from these galaxies caused by intervening dark matter, a phenomenon called weak gravitational lensing. By combining these immense datasets, Roman will provide the most detailed picture yet of how dark energy has behaved across cosmic history, potentially revealing whether it is a constant force or something that changes over time, which would completely reshape our fundamental theories of physics. Beyond this grand cosmological quest, the Roman telescope has a second, equally exciting mission: a galactic exoplanet census on a scale we can barely imagine. While the Kepler mission taught us that planets are common and TESS is finding them around our nearest stellar neighbors, Roman will find planets in a way no other telescope can through a phenomenon called microlensing. This occurs when the gravity of a star or planet acts as a natural lens, briefly bending and magnifying the light from a more distant star behind it. If the foreground star has a planet, that planet will create its own distinct blip in the light curve. The beauty of microlensing is its power to find planets that are otherwise invisible, especially those that are cold, icy, or located far from their star in the frigid outer reaches of their solar systems, places analogous to our own Kuiper belt. Roman's wide field view will allow it to continuously monitor hundreds of millions of stars toward the crowded center of our galaxy, where microlensing events are most common. It's predicted to discover thousands of new worlds, many of them with masses and orbits similar to those in our own solar system, finally giving us a statistically complete picture of the architecture of planetary systems across the galaxy. This incredible observatory will also serve as a premier tool for general infrared astrophysics, its large field of view making it a powerful discovery machine. It will conduct deep surveys of the universe to study the formation and evolution of galaxies, peer through the dust that obscures stellar nurseries to watch stars being born, and hunt for isolated rogue planets drifting alone in the darkness between stars. Its coronagraph instrument, an advanced technology demonstration, will push the boundaries of direct imaging by blocking the blinding light of nearby stars to reveal the faint planets orbiting them. This tech will be a critical pathfinder for future missions designed to directly photograph Earth-like worlds. By painting the universe in such broad, deep strokes, the Nancy Grace Roman Space Telescope will not only answer specific questions about dark energy and exoplanets, but will undoubtedly make discoveries we haven't even thought to look for, uncovering new cosmic phenomena that will once again redefine our place in the cosmos. Leaving behind the frigid, methane-soaked landscapes of Titan, we now venture inward toward the Sun, to a world that presents a stark and terrifying warning. Venus is Earth's twin in size and mass, a sibling world born from the same cosmic materials. Yet its evolution took a catastrophic turn, transforming it into a scorching, toxic inferno with surface temperatures hot enough to melt lead and pressures that crush like the deepest ocean trench. For decades, this hellish environment has repelled our probes after mere hours on the surface. But now, after a long hiatus, we are going back not to endure its surface, but to understand its story. NASA Veritas mission, Venus Emissivity, Radio Science in SAR, topography, and spectroscopy represents a sophisticated orbital effort to peel back the planet's thick, acidic clouds and finally answer a haunting question: what happened to our sister planet? The key to unlocking Venus's secrets lies in seeing through the obscuring veil that has hidden its surface from our view for so long. Veritas will achieve this with a powerful suite of instruments, chief among them a state-of-the-art synthetic aperture radar system. This technology will allow the orbiter to map the entire surface of Venus at a resolution and clarity we've never before achieved. Imagine the difference between a blurry, hand-drawn map and a high-definition satellite image. That's the leap in detail Veritas will provide. It will chart topography with such precision that we could identify a hill or valley the size of a small town, finally revealing the true character of the Venusian landscape. This unprecedented view is expected to revolutionize our understanding of the planet's geology. A central question Veritas will tackle is whether Venus is still geologically alive. Does it have active volcanoes, shifting tectonic plates, or moving crustal blocks? While we see a young surface unblemished by many craters because of constant volcanic resurfacing, we don't know if this activity is ongoing or happened in a distant, violent past. The radar will be so sensitive it could detect the subtle changes in topography caused by a volcanic eruption or a fault slip that occurred during the mission itself. It will also hunt for the telltale signatures of hotspots, areas where magma might be close to the surface, suggesting the planet's internal engine is still running. Complementing the radar is a near-infrared spectrometer, a crucial instrument for determining the composition of Venus's surface rocks. Because the surface is so inhospitable, we have very few direct measurements of what it's actually made of. Different minerals emit their own unique thermal signatures, and this spectrometer will be able to detect those fingerprints through the lower atmosphere, particularly on mountaintops where the air is slightly thinner. This data is vital. If we find rocks like granite which form in the presence of water, it would be monumental evidence that Venus once had vast oceans, a key ingredient for a habitable past. Understanding the rock composition will tell us about the planet's volcanic history and the conditions that shaped its surface. The grand, overarching goal of Veritas is to reconstruct the entire climate history of Venus and determine why it became a runaway greenhouse nightmare while Earth flourished. By creating a global, high-resolution geologic map, scientists will be able to piece together the sequence of events. Did a period of intense volcanism billions of years ago pump so much carbon dioxide into the atmosphere that it triggered an unstoppable greenhouse effect, boiling away any oceans it might have had? Or was its proximity to the sun always a death sentence, with water vapor in its early atmosphere trapping heat from the start and sealing its fate? The answers Veritas provides will extend far beyond our solar system. As we discover thousands of exoplanets, many of them Earth-sized worlds orbiting in the so-called habitable zones of their stars, Venus stands as a critical cautionary tale. It proves that size and location alone are not enough to guarantee a livable world. A planet's geologic activity, its volcanism, its plate tectonics, its ability to recycle carbon, may be the deciding factor between a temperate Earth and a scorching Venus. This mission will give us the data to build better models for planetary evolution, helping us identify which exoplanets are truly promising candidates for life and which are merely Earth-sized hellscapes. Veritas is more than a mission to Venus. It is a quest to understand the delicate balance that makes a planet a home, and in doing so, it will teach us to better appreciate our own. While Veritas works from orbit to map the history written on Venus's surface, another mission is taking the direct approach, plunging straight into the storm to read the story written in the air itself. JWST, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, is a daring descent probe designed to do something we haven't attempted in over 40 years. Survive a fall through Venus's crushing, acidic atmosphere and send back data all the way down. This isn't just a repeat of past efforts, it's a technological marvel equipped with instruments of incredible sensitivity, built to answer questions that have lingered since the first Soviet probes briefly transmitted from the Inferno. The mission begins with a carrier spacecraft that will first perform 2 flybys of Venus, using its instruments to study the planet's clouds and map surface composition in the ultraviolet spectrum, scouting for interesting features. But the main event is the descent sphere, a rugged, titanium-clad probe about 3 feet across that will be released into the Venusian atmosphere. For the next hour, as it falls toward the surface, this sophisticated laboratory will experience a transformation of environment unlike any other in the solar system. It will start in the cool, hazy upper layers and plunge into increasingly dense, hot, and corrosive conditions, all while conducting a layer-by-layer chemical analysis of the air itself. This vertical profile is the key that Veritas, from its orbital perch, cannot provide a direct measurement of how the atmosphere changes from top to bottom. The probe's suite of instruments is specifically tuned to hunt for clues about Venus's watery past. Chief among its targets are the noble gases elements like krypton, xenon, and argon. These gases are inert, they don't react with other elements or get locked away in rocks. They are cosmic time capsules preserving a record of the early conditions from when the planet first formed. The precise ratios of different isotopes of these gases can tell scientists whether Venus started with a similar inventory of water and other volatiles as Earth. If the ratios match, it strongly suggests Venus was once a much wetter, more temperate world. If they differ, it points to a fundamentally different origin story. This is forensic science on a planetary scale, and I will be the first mission precise enough to make these definitive measurements, but the probe's work doesn't stop at gases. As it descends, it will also use a specially designed instrument, the Venus Tunable Laser Spectrometer, to sniff out specific chemical compounds in the lower atmosphere. It will be searching for traces of gases that shouldn't be there if the planet has been a dry inferno for billions of years. The Holy Grail would be finding phosphine, a gas that on Earth is almost exclusively produced by microbial life or industrial processes. Its tentative detection from Earth-based telescopes a few years ago caused a major stir, and while those findings are heavily debated, I will be in a position to settle the argument once and for all by measuring it directly. Even if it doesn't find phosphine, detecting other trace gases will help us understand the complex chemical processes currently underway in the atmosphere. Perhaps the most visually stunning part of the mission will occur during the final few kilometers of the descent. As the probe drops below the thickest cloud layers, a hardened window will allow a camera system to look downward. It will begin capturing hundreds of high-resolution images of the surface during its fall, photographing a region known as Alpha Regio. This is a rugged highland area, and scientists believe its complex tectonic features could hold evidence of past interactions with water. These will not be the fuzzy, low-contrast images from the Soviet Venera landers. This will be our first clear, panoramic view of the Venusian landscape, revealing the texture of the rock and the geology of the terrain in stunning detail, right up until the moment the probe likely succumbs to the extreme surface conditions. Together, Veritas and DaVinci form a powerful tag team for Venusian science. Veritas provides the global context, the wide-angle view of the planet's history written in its rocks and mountains. DaVinci provides the intimate ground truth details, the chemical fingerprints trapped in the air, and the first clear pictures of the surface in generations. One mission looks at the what and where of Venus's geology, while the other investigates the how and when of its atmospheric evolution. Their combined data will allow us to write the definitive biography of Earth's twin, answering whether it was once a blue world with oceans and a temperate climate, and precisely what chain of events turned it into the warning it is today. A story of planetary evolution that holds profound lessons for our understanding of climate, habitability, and the fate of worlds everywhere. Venturing now from the shrouded planets of the inner solar system, we set our sights on a destination unlike any other we have ever visited, a world not of rock or ice but of metal. Floating in the main asteroid belt between Mars and Jupiter is an object called 16 Psyche. From afar, it appears as little more than a faint star, but radar observations have revealed its astounding truth. This asteroid is incredibly dense and reflects light like polished metal. The leading hypothesis is that 16 Psyche is the exposed, naked core of a protoplanet, a planetary building block that had its rocky outer layers violently stripped away by colossal impacts during the solar system's chaotic infancy. We have never seen anything like it. This mission is our first and only chance to directly study a planetary core, offering a window into the fiery, violent processes that shape the terrestrial worlds, including our own Earth. The journey to this metal world is a feat of engineering in itself. The Psyche spacecraft, launched in October 2023, is not taking a direct route. To reach the asteroid belt, it is employing a tremendously efficient but slow form of propulsion, solar electric propulsion. Two massive solar arrays, each as long as a tennis court, convert sunlight into electricity, which is then used to power powerful thrusters that accelerate electrically charged atoms of xenon gas to tremendous speeds, creating a gentle but continuous thrust. This allows the craft to build up incredible velocity over time without needing to carry vast amounts of heavy chemical fuel. Its path is also being assisted by a gravity slingshot from Mars in 2026, using the planet's gravity to curve its trajectory toward its final destination, with arrival expected in August of 2029. Once it arrives, the spacecraft will enter orbit around this strange metal world for a 21-month primary mission, and its suite of instruments is custom-built to solve the mysteries of Psyche's origin. A multispectral imager will capture the first high-resolution pictures of the surface. Scientists don't expect to see familiar craters and mountains. Instead, they anticipate a bizarre landscape of metal cliffs, solidified metal lava flows called ferrovolcanism, and giant metal spikes that may have formed in the vacuum of space. The images will also search for any remnants of the original rocky mantle that might still be clinging to the metallic surface, which would be a crucial clue to the object's history. To determine the asteroid's true composition and structure, the orbiter carries a gamma-ray and neutron spectrometer. This instrument will essentially taste the surface from orbit, measuring the energy of particles emitted from Psyche after it is bombarded by cosmic rays. Each element has a unique signature, allowing the instrument to map the distribution of key metals like iron, nickel, and platinum, as well as any silicate rocks that might be present. This data will definitively answer whether Psyche is truly a pure metal core, or perhaps a rare, primordial type of metal-rich asteroid that formed in a different way. A magnetometer on board will be listening carefully for any remnant magnetic field frozen within the metal. If the protoplanet that Psyche once belonged to had a molten, churning core like Earth's, it would have generated a magnetic field. Evidence of that ancient field preserved in the metal structure would be the ultimate proof that this is indeed a fossilized planetary core. The profound implications of this mission reach to the very heart of planetary science. We have models for how planets like Earth formed, with their layered structures of core, mantle, and crust, but these are based on indirect evidence. We infer the properties of our own planet's core by studying seismic waves that travel through it. Psyche offers a completely different approach: direct observation. By studying this one exposed core, we can test our theories about the building blocks of planets, the process of planetary differentiation where heavy metals sink to the center, and the incredible violence of the early solar system where such colossal collisions were common. The mission could confirm our fundamental understanding of planet formation, or it could reveal something entirely unexpected, forcing us to rewrite the textbooks on how rocky worlds are built. By visiting this metallic relic, we are not just exploring an asteroid, we are undertaking a form of interstellar archaeology, digging into the deepest, most hidden layer of a planet's history to understand the secret recipe that created our own world. As we shift our gaze from distant asteroids back to our celestial neighbor, the Moon, we encounter not just another mission, but the very cornerstone of a new era in space exploration. The Lunar Gateway represents a fundamental shift in how we approach deep space, moving from short-term expeditions to establishing a permanent, sustainable foothold beyond Earth's orbit. This isn't a simple space station. It's a strategically positioned outpost that will orbit the Moon in a unique, highly elliptical path known as a near-rectilinear halo orbit. This special orbit offers incredible advantages, providing both stable long-term access to the lunar surface and a continuous line of sight for uninterrupted communication with Earth, making it the perfect staging ground for the next chapter of human exploration. The architecture of the Gateway is a testament to international cooperation and modular design. Unlike the International Space Station, which required dozens of complex assembly flights, the Gateway is being designed from the start with sustainability and flexibility in mind. Its core will consist of two foundational elements provided by NASA: the Power and Propulsion Element, and the Habitation and Logistics Outpost, or HALO. The Power and Propulsion Element is the station's beating heart and brain, a high-power 40-kilowatt solar electric propulsion spacecraft that will provide all the station's power, communications, and the ability to maintain its unique orbit for years. Docked to this will be the HALO module, which serves as the initial crew cabin, featuring docking ports for visiting spacecraft like Orion and future logistics modules, and providing the basic life support and command functions for the first crews. This initial foundation will quickly grow into a truly international complex. The European Space Agency is contributing a critical element called the International Habitation Module, or IHAB, which will significantly expand the living and working space for astronauts, featuring an additional life support system to recycle air and water. The Canadian Space Agency is building the next generation of its iconic robotic technology, the Canadarm3. This smart robotic system will be essential for maintaining the station, capturing visiting vehicles, and assisting astronauts during spacewalks, all while operating with a high degree of autonomy given the station will be uncrewed for much of the year. Japan's space agency, JAXA, is also contributing with its own habitat module, further enhancing the station's capabilities and ensuring a global partnership is literally built into its structure. The scientific potential of this orbital laboratory is immense. Positioned far outside the protective bubble of Earth's magnetosphere, the Gateway will be an unparalleled platform for heliophysics and radiation studies. Astronauts will be able to directly observe the Sun and deep space without atmospheric interference, monitoring solar storms and cosmic rays in ways impossible from Earth orbit. This research is not just academic, it is absolutely critical for understanding the long-term health risks astronauts will face on years-long missions to Mars and for developing the better shielding and protective technologies they will need to survive. The station will also serve as a remote command post for operating rovers and other robotic assets on the lunar surface in near real time, a capability that will be vital for scouting landing sites and conducting science in areas too dangerous or difficult for humans to reach initially. Perhaps the Gateway's most vital role is that of a technology testbed and a proving ground for the deep space survival skills we must master before venturing to Mars. Every system on board, from advanced life support that recycles 98% of the station's water to novel radiation shielding materials, is a prototype for the technologies that will be required for a multi-year journey to the Red Planet. The station will also be the home base for the human landing systems that will ferry astronauts down to the lunar surface. Instead of a single, massive spacecraft launching from Earth to the Moon and back, the Gateway enables a more efficient, sustainable model. Astronauts will arrive from Earth on an Orion capsule, transfer to a reusable lander docked at the Gateway, descend to the surface for their expedition, return to the Gateway to resupply and switch crews, and then board an Orion for the return trip to Earth. This lunar hub model drastically reduces the amount of fuel and mass that needs to be launched from Earth's deep gravity well, making regular lunar travel economically and logistically feasible for the first time. By learning to live and work in deep space just a few days from Earth, we are creating the blueprint for the first human mission to Mars. The Gateway is where we will validate the deep space habitation systems, operational procedures, and crew resilience needed for a journey that will be 1,000 times farther and 100 times longer. It is the essential stepping stone, the necessary practice run before we commit to that greatest of adventures. This international outpost is more than a collection of modules. It is the first true spaceport beyond our planet, a symbol of global partnership and a gateway not just to the Moon, but to the entire solar system. But to truly become an interplanetary species, we need more than just an outpost. We need a fleet. And that fleet is now taking shape not in a government facility, but on the coastal plains of South Texas. Here, SpaceX is relentlessly developing a spacecraft so audacious in its scale and ambition that it seems pulled from the pages of science fiction, Starship. This isn't just another rocket, it's a fundamental reimagining of spaceflight itself, a fully reusable super heavy lift system designed with one ultimate goal in mind, to make humanity a multi-planetary civilization. The most radical aspect of Starship is its core philosophy, complete and rapid reusability. Every orbital-class rocket in history, with the partial exception of SpaceX's own Falcon 9, has been designed as expendable. Their components, costing hundreds of millions of dollars, are used once and then discarded, burning up in the atmosphere or sinking into the ocean. This is the primary reason spaceflight has remained so prohibitively expensive. Starship shatters that paradigm. The entire system is built to be refueled and reflown again and again, much like a commercial airliner. The booster, known as Super Heavy, will launch the spacecraft to orbit and then return to its launch mount, caught by mechanical arms to be inspected, refueled, and launched again, potentially within hours. The Starship spacecraft itself is designed to survive the fiery re-entry into Earth's atmosphere, landing vertically to be prepared for its next mission. This paradigm shift from building a new car for every cross-country trip to simply refueling the family sedan is what promises to reduce the cost of accessing space by orders of magnitude. The statistics behind this vehicle are almost incomprehensible. When fully stacked, Starship stands nearly 400 feet tall, making it the largest and most powerful launch vehicle ever created. Its booster is powered by a staggering 33 Raptor engines, a new full-flow staged combustion engine that runs on liquid methane and liquid oxygen. This combination offers a great balance of performance and practicality, and crucially, methane can potentially be synthesized from the Martian atmosphere and water ice, meaning Starship could refuel on Mars for its return journey to Earth. The payload capacity is equally mind-boggling. In its reusable configuration, it's designed to loft well over 100 metric tons to orbit. In an expendable version, that number could double. To put that in perspective, it could launch the entire mass of the International Space Station in a handful of flights. This immense capacity completely changes what we can send into space. Massive space telescope mirrors, entire segments of future space stations, or the vast amounts of cargo needed to build a base all in a single launch. This capability is the key that unlocks the solar system. For the Moon, Starship has been selected as a human landing system for the Artemis Program. A specialized lunar variant will act as a lander, departing from the lunar gateway to carry astronauts and tens of tons of supplies down to the surface. Its massive payload bay could deliver habitats, rovers, and power systems in one go, jump-starting the construction of a permanent lunar base, but the Moon is just the proving ground. The true destination is Mars. A fleet of Starship vehicles would journey to the Red Planet during the orbital alignment windows that occur every 26 months. Their goal would be to transport not just a few astronauts on a flags and footprints mission, but the critical infrastructure for a self-sustaining city. We're talking about entire industrial plants for producing water, oxygen, and methane fuel, fleets of robotic rovers for construction, hydroponic farms for food, and large-scale habitats to shield colonists from radiation. The vision extends far beyond these government-led endeavors. By dramatically slashing the cost to orbit, Starship aims to democratize access to space in a way we've never seen. It could enable large-scale space manufacturing, taking advantage of microgravity to create new alloys, pharmaceuticals, and fiber optics that are impossible to produce on Earth. It could finally make large-scale space tourism a reality, with its spacious payload area reconfigured to carry dozens of passengers on point-to-point flights around Earth or on week-long journeys orbiting the planet. Some concepts even suggest it could fulfill Elon Musk's original inspiration for the project. transporting people between cities on Earth in under an hour, turning a 15-hour flight from New York to Tokyo into a journey of less than 60 minutes. Of course, the path to realizing this future is paved with immense technical challenges. The process of orbital refueling, where one Starship must safely transfer hundreds of tons of cryogenic fuel to another in orbit, is an untested and complex dance that is absolutely essential for Mars missions. The heat shield system, composed of thousands of hexagonal tiles, must reliably protect the spacecraft during atmospheric re-entry from orbital and even interplanetary velocities. The sheer logistics of launching, landing, refueling, and relaunching a vehicle of this scale with airline-like frequency represents a hurdle unlike any yet overcome in aerospace history. Every test flight, whether it ends in a successful landing or a spectacular explosion, provides invaluable data that accelerates the development cycle through rapid iteration. The successful development of Starship would represent more than just a new rocket. It would be a fundamental inflection point in human history. It is the first vehicle designed from the ground up not merely to explore space, but to enable us to live there. It transforms the concept of off-world colonization from a distant dream discussed in conference halls into a tangible engineering project with a clear, albeit challenging, path forward. It promises to break the cycle of expensive, one-time use hardware and open the cosmic coastline to a wave of exploration, industry, and settlement. This isn't just about building a spacecraft, it's about building a bridge to the future of humanity. While we look to the Moon and Mars as the next frontiers for human exploration, some of the most promising habitats for life in our solar system lie far beyond orbiting a giant. The European Space Agency's J-Jupiter Icy Moons Explorer, or JWST, is a mission of profound astrobiological significance, setting its sights not on the gas giant Jupiter itself, but on its fascinating ice-encased lunar companions. This ambitious spacecraft is designed to conduct the most comprehensive investigation ever undertaken of three worlds that may harbor vast, hidden oceans: the complex and captivating moons Ganymede, Callisto, and Europa. By studying these frozen realms and their dramatic interactions with their colossal parent planet, JWST aims to answer one of science's most compelling questions: could life have found a way in the cold, dark depths of the outer solar system? The mission's ultimate prize is Ganymede, the largest moon in the solar system, even bigger than the planet Mercury. But its most intriguing feature is hidden from view: a colossal subsurface ocean, believed to hold more water than all of Earth's oceans combined. What makes Ganymede truly unique, however, is that it is the only moon known to generate its own magnetic field, a miniature planet-like force field that is embedded within Jupiter's immensely powerful magnetosphere. This creates a complex and dynamic interaction, a cosmic dance of magnetic forces that JWST will study in exquisite detail. The mission will spend 9 months dedicated to orbiting Ganymede itself, mapping its surface, sounding its interior, and unraveling the mysteries of its magnetic heart to understand how this world maintains a liquid ocean and whether it possesses the necessary conditions for habitability. To unlock these secrets, the JWST spacecraft is a marvel of scientific instrumentation, carrying 10 advanced tools perfectly suited for this challenging environment. A powerful laser altimeter will fire pulses at the surface to measure the subtle tidal deformations of Ganymede's icy crust. As the moon orbits Jupiter, the giant planet's gravity flexes it, causing the surface to bulge and relax. By precisely measuring the amplitude of these bulges, scientists can infer the thickness of the ice shell and the depth and salinity of the ocean beneath, essentially using gravity to weigh and probe an alien sea. A sophisticated ice-penetrating radar system will perform a similar function from orbit, sending radio waves through the ice to directly measure the shell's thickness and search for pockets of liquid water closer to the surface. The mission's suite of cameras and spectrometers will work in concert to map the geological and chemical composition of the Moon's surfaces in unprecedented detail. High-resolution images will chart the complex terrain of Ganymede with its strange mix of dark, ancient, cratered regions and brighter, younger grooves and ridges, telling the story of its geological evolution. An ultraviolet spectrograph will study the thin atmospheres or exospheres of these moons, which are created when charged particles from Jupiter's magnetosphere smash into the surface ice, kicking atoms and molecules into space. By analyzing the composition of these tenuous gases, scientists can deduce the chemistry of the ice below. This interaction with Jupiter's ferocious radiation belts is a double-edged sword. The same energetic particles that erode the surface also provide a potential energy source for chemistry and possibly even biology in the subsurface oceans. A magnetometer and a powerful particle environment package onboard JWST will meticulously chart the flow of energy and material within the Jupiter system. They will measure how Jupiter's magnetic field funnels particles onto the moons, how those particles alter the surface ice to create new compounds, and how some of those materials might eventually make their way down into the dark oceans below, potentially providing the nutrients needed to sustain life. Before it can settle into orbit around Ganymede, JWST will conduct a grand tour of the Jovian system, performing 25 flybys of all 3 icy moons. This includes 2 close passes of Europa, which will allow it to add crucial data to that being gathered by NASA Europa Clipper mission, particularly measuring the thickness of its icy crust and searching for signs of its famous water plumes. It will also make 12 flybys of the ancient, heavily cratered moon Callisto. Thought to be the most geologically dead of the 3, Callisto's pristine surface is a record of the earliest history of the solar system. Yet, evidence also suggests it too hides a subsurface ocean, making it a fascinating example of how a seemingly inert world can still possess a potentially habitable environment. The journey itself is a monumental feat of navigation and patience. Launched in April 2023, the spacecraft will take 8 years to reach Jupiter, using gravity assists from Earth and Venus to slingshot itself into the outer solar system. Once it arrives in 2031, its mission of at least 4 years will begin, a testament to long-term planning and international cooperation in the pursuit of knowledge. By the time JWST concludes its investigations, we will have a complete picture of the Jupiter system, not just as a giant planet with moons, but as a complex mini-solar system in its own right, with Ganymede as a central world worthy of study in its own right. This mission will transform these points of light into fully realized worlds, assessing their potential as abodes for life and forever changing our understanding of where living organisms might thrive in the universe. While we often think of our most powerful telescopes as being trained on specific, distant targets, sometimes the biggest discoveries come from looking at absolutely everything. Enter SPHEREX, the spectrophotometer for the history of the universe, epoch of reionization and ICE's explorer. This remarkable NASA mission is pursuing a goal of breathtaking scope and ambition: to create the first all-sky spectroscopic map in near-infrared light. Imagine a cosmic cartographer tasked with creating a 3-dimensional atlas of the entire heavens, one that doesn't just show where things are, but what they are made of. That is the monumental undertaking of SPHEREX, and the data it collects promises to touch upon nearly every major question in modern cosmology and astronomy. The sheer scale of this survey is difficult to comprehend. Over its 2-year planned mission, SPHEREX will observe over 300 million galaxies and 100 million stars within our own Milky Way. It will do this not by staring intently at one small patch of sky, but by continuously scanning, slowly rotating to sweep across the entire celestial sphere. It will map the whole sky not once, but 96 separate times, creating overlapping layers of data that will allow scientists to build up an incredibly detailed and comprehensive catalog. This method is what allows it to achieve its primary objective, creating a three-dimensional map of the universe. Unlike a photograph that shows a flat, two-dimensional projection, SPHEREX will use spectroscopy to measure the redshift of each galaxy it sees. Because the universe is expanding, the light from more distant galaxies is stretched into longer, redder wavelengths. By precisely measuring this redshift, astronomers can calculate the distance to each galaxy, transforming a flat picture into a deep, volumetric map of cosmic structure stretching back over 10 billion years. This three-dimensional map will serve as a powerful machine for probing the very first moments of existence. One of SPHEREX's key science goals is to search for the faint imprint of cosmic inflation, that theorized period of faster-than-light expansion that occurred in the first fraction of a second after the Big Bang. The theory predicts that this violent expansion would have generated primordial gravitational waves, ripples in the fabric of space-time that would have subtly influenced how galaxies were distributed in the early universe. This pattern would be incredibly faint, buried within the large-scale structure of the cosmos. By mapping the precise positions and distances of hundreds of millions of galaxies, SPHEREX will have the statistical power to search for this faint signal. Finding it would provide our first direct observational evidence for inflation, confirming a cornerstone of our cosmological models and giving us a glimpse into the universe when it was less than a second old. But the mission's gaze is not only fixed on the impossibly distant and ancient, it will also turn its spectroscopic eye on our own cosmic neighborhood, studying the processes that lead to the formation of planetary systems. As it scans the sky, SPHEREX will observe the disks of gas and dust swirling around countless young stars. Its near-infrared spectrometers are exquisitely tuned to detect the chemical fingerprints of water ice and frozen organic molecules trapped within these dusty cradles of planet formation. The presence and abundance of these ices are crucial ingredients for life as we know it. By creating a vast census of which stars are surrounded by these life-giving materials, and in what quantities, scientists can begin to understand how common the basic building blocks of planets and potentially life might be throughout the galaxy. This survey will tell us if the availability of water and organics is a rare cosmic circumstance or a standard part of the stellar nursery package. The true power of SPHEREX lies in its unique combination of breadth and precision. Previous all-sky surveys, like those conducted by WISE or Planck, provided incredible maps but lacked the detailed spectroscopic data that SPHEREX will deliver. Other powerful spectroscopic missions, like the James Webb Space Telescope, provide incredibly deep and detailed looks at tiny areas of the sky. SPHEREX occupies a vital middle ground, offering a wide-angle spectroscopic view of the entire universe. It is this panoramic yet detailed perspective that will make its dataset a treasure trove for astronomers for decades to come, a fundamental resource that will provide the context for more focused observations and likely lead to discoveries we haven't even thought to look for yet. It is a mission designed to see the forest and the trees, charting the grand architecture of the cosmos while simultaneously taking an inventory of the very materials that make worlds like our own possible. While many missions spend years traveling to a predetermined destination, one ambitious project is taking a completely different approach, embracing patience and opportunism on a cosmic scale. The Comet Interceptor, led by the European Space Agency with support from JAXA, is a mission designed to lie in wait for a visitor from the farthest reaches of our solar system, or even beyond. Its target is not a known comet, but a pristine one, an object that has never before ventured into the warmth of the inner solar system. These ancient relics have been preserved in a deep freeze since the dawn of our planetary system, and by intercepting one, we have a chance to examine the unaltered building blocks of planets in their original state, a sample of the solar system's raw ingredients that has been kept perfectly fresh for 4.6 billion years. The challenge, of course, is that we don't yet know the identity of this target. Long-period comets or even interstellar objects like Oumuamua arrive with little warning, often giving us only a few months to prepare before they swing around the Sun and depart forever. To solve this problem, the Comet Interceptor will use a clever staging strategy. After launch, it will not head toward a specific object. Instead, it will journey to a gravitational parking spot in space known as the Sun-Earth Lagrange Point 2, or L2, the same stable orbital location shared by the James Webb Space Telescope. Here, it can remain in a stable orbit with minimal fuel expenditure for years, patiently waiting for the perfect target to be discovered by ground-based telescopes. Once astronomers identify a suitable pristine comet or interstellar object on its inbound journey, the waiting game ends. The mothership will then leave its parking spot and embark on a high-speed intercept course. This is where the mission's innovative design truly shines. The main spacecraft does not carry a single set of instruments. It carries 3 separate spacecraft in a single launch. As it approaches the target, it will release these 3 probes to perform a coordinated flyby from different angles and distances. This multi-point observation strategy is a first for comet science and is crucial for building a complete 3-dimensional picture of the object's activity. The trio of spacecraft each have a specialized role. The main mothership, provided by ESA, will operate at a safer distance, performing overall coordination and capturing the broader context of the comet and its developing coma, the cloud of gas and dust that erupts from the nucleus as it is heated by the Sun. A smaller companion spacecraft, also built by ESA, will venture much closer to the nucleus to take incredibly high-resolution images and analyze the composition of the coma with its own suite of instruments. The third element, a smaller probe contributed by JAXA, will get closest of all, potentially flying within just a few hundred kilometers of the nucleus. Its mission is especially daring, to measure the complex interactions between the comet's emitted gas and the solar wind, the stream of charged particles flowing from the Sun. Flying through this dynamic and dusty environment is a tremendous risk, but the reward is a dataset that cannot be acquired from a safe distance. What makes a pristine comet so scientifically valuable is its profound purity. Short-period comets, like the one visited by the Rosetta mission, have made many trips around the Sun. Each pass cooks their surface, vaporizing their most volatile ices and leaving behind a crusty, altered layer of dust and organic material that masks their original composition. A truly pristine long-period comet, however, is falling sunward for the very first time. Its surface ices are still fresh, and the gases erupting from its interior provide a direct sample of the material that existed in the outer protoplanetary disk when the solar system was forming. Analyzing this material is like opening a time capsule that has been sealed since before the planets even existed. The scientific instruments on board the 3 spacecraft are designed to perform a comprehensive chemical analysis of this primordial stuff. They will identify the specific ratios of different isotopes in the water ice and other gases, which can tell us where and how the comet formed in the early solar system. They will detect complex organic molecules, the carbon-rich building blocks of life, to see if comets could have delivered these essential ingredients to the early Earth. By studying the dust particles ejected from the nucleus, they can determine the physical structure and composition of the solid material that eventually coalesced into planets. The potential for a truly extraordinary discovery is always present. The mission is also designed to be able to intercept an interstellar object, should one like Oumuamua or Borisov be discovered on a suitable trajectory. Studying such an object would be an unprecedented opportunity to directly analyze material from another star system, offering our first glimpse into the building processes of worlds orbiting other suns. Whether it chooses a pristine solar system comet or an interstellar visitor, the Comet Interceptor represents a new class of mission, one that is agile, patient, and ready to seize a unique chance encounter. It is a celestial ambush planned with meticulous care, waiting in the dark for the perfect moment to reveal secrets from the very beginning of everything. While we've been exploring distant worlds and cosmic mysteries, there's a very practical, Earth-focused reason to look up at the sky. Our planet exists in a cosmic shooting gallery. The threat of a catastrophic asteroid impact isn't just a plot for a blockbuster movie. It's a real, albeit low probability, event that has shaped the history of life on Earth and will inevitably happen again. The key to our survival isn't hiding in bunkers, but in finding these potential threats with enough advance warning to do something about them. This is the critical mission of NEO Surveyor, the Near-Earth Object Surveyor Space Telescope, a dedicated sentinel designed to protect our planet by completing the inventory of dangerous asteroids and comets. The challenge in planetary defense is that space is vast, and many asteroids are incredibly dark, absorbing most of the sunlight that hits them and reflecting very little back toward Earth. This makes them nearly invisible to optical telescopes, especially those that must peer through the bright backdrop of our own atmosphere. What these dark, carbon-rich asteroids lack in visible reflectivity, however, they make up for in heat. All objects in space absorb energy from the sun and re-radiate it as heat in the infrared part of the spectrum. A dark asteroid that is virtually invisible to an optical telescope will glow brightly in infrared light. NEO Surveyor is specifically designed to see this thermal emission, allowing it to detect asteroids based on their temperature and size rather than their reflectivity, effectively turning on the lights in the dark corners of our solar system. This infrared space telescope will operate from a unique vantage point at the Sun-Earth Lagrange Point 1, a gravitationally stable spot between Earth and the Sun. From this position, it can continuously scan the sky near the Sun, an area notoriously difficult to observe from Earth because it is only visible during the brief twilight periods of dawn and dusk. This is a critical blind spot, as many asteroids that cross Earth's orbit, known as ATONs, spend a significant portion of their time interior to Earth's orbit closer to the Sun. By having an unobstructed 24/7 view of this region, NEO Surveyor will find objects that have, until now, remained hidden in the glare. Its mission parameters are both clear and ambitious: to discover and characterize 90% of near-Earth objects larger than 140 meters in diameter within its first decade of operation. This size threshold is a crucial line in the cosmic sand. An impact from an object this large would not be a local event. It would have continental-scale consequences, releasing energy equivalent to hundreds of megatons of TNT and potentially causing a nuclear winter effect that could devastate agriculture and ecosystems worldwide. Completing this census is a foundational step in planetary defense, as you cannot mitigate a threat you do not know exists. The power of NEO Surveyor lies not just in finding these objects, but in precisely tracking them. Its sensitive infrared detectors will allow it to measure an asteroid's size and composition with remarkable accuracy simply by analyzing its heat signature. This is vital information for planning any potential deflection mission. The strategy needed to gently nudge a solid rock off course is very different from the approach required for a loose rubble pile. Furthermore, by observing an object's position over multiple nights, the telescope can precisely calculate its orbit for decades, even centuries into the future. This long lead time is the most valuable asset in our planetary defense toolkit. With decades of warning, a range of deflection technologies become feasible. A kinetic impactor like NAS, a successful DRRT mission, could be sent to collide with the asteroid, slightly altering its velocity over many years to ensure it misses Earth. More advanced concepts like a gravity tractor, a spacecraft that would fly alongside the asteroid and use its own tiny gravitational pull to slowly tug it off course, could also be deployed. These are gentle, controlled methods, but they require time to work. NEO Surveyor provides that time, transforming a potential global catastrophe from an unavoidable act of nature into a manageable engineering problem. The data it collects will do more than just identify threats. It will also provide a treasure trove of scientific information about the formation and evolution of our solar system. These near-Earth objects are fragments from its early days, and by studying their sizes, compositions, and orbital distributions, scientists can piece together the history of planetary migration and the bombardment that delivered water and organic materials to the early Earth. In this way, NEO Surveyor embodies a beautiful duality. It is a mission focused on safeguarding the future of our civilization while simultaneously uncovering the secrets of our ancient past. It is our global insurance policy, a vigilant guardian ensuring that the story of humanity does not end with an unexpected and uninvited guest from the depths of space. While our current telescopes can infer the presence of an atmosphere around a distant world, the next leap demands something far more profound: the ability to directly see and study a pale blue dot orbiting another star. This is the monumental goal of LUVOIR, the Large Ultraviolet Optical Infrared Surveyor. More than a mere telescope, LUVOIR is a vision, a concept for a flagship observatory so powerful it would not only find planets like Earth but also photograph them in stunning detail, analyzing their light for the telltale signs of a living world. It represents the culmination of decades of astronomical progress, a machine designed to answer a question that has haunted humanity since we first looked up: are we alone? To appreciate LUVOIR's ambition, one must first understand its sheer physical scale. The James Webb Space Telescope's 6.5-meter gold-coated mirror was a revolutionary feat of engineering. LUVOIR, in its most ambitious design, would dwarf it, featuring a segmented primary mirror stretching an astonishing 15 meters across. To put that in perspective, its light-gathering area would be over 5 times larger than Webb's. This colossal size is not for show, it is the fundamental key to its mission. Resolving a small, Earth-sized planet orbiting in the habitable zone of its star is like trying to photograph a firefly hovering next to a massive searchlight from thousands of miles away. The starlight is billions of times brighter than the faint glimmer of the planet, utterly overwhelming it. LUVOIR's vast mirror is designed to collect enough of that incredibly faint planetary light to make it detectable, while its advanced internal systems work to systematically cancel out the blinding glare of the parent star. This brings us to the second revolutionary technology LUVOIR would employ: an advanced coronagraph and potentially an accompanying starshade. A coronagraph is an internal instrument that acts like a highly sophisticated thumb blocking a bright light. It uses a series of complex masks and mirrors to physically block the intense light of the star, while allowing the much fainter light from the orbiting planets to pass through to the detectors. The engineering required is breathtaking, needing to suppress the starlight by a factor of over 10 billion. An alternative or complementary technology is a starshade, a separate flower-shaped spacecraft that would fly tens of thousands of kilometers in front of the telescope, precisely positioning itself to cast a shadow on the telescope, perfectly blocking the starlight and allowing the planets to shine through. Both concepts represent the cutting edge of optical physics, turning a theoretical possibility into a practical tool for discovery. With these technologies working in concert, LUVOIR would transition exoplanet science from inference to direct observation. Instead of detecting planets by the slight dip in starlight as they transit or the wobble they impart on their star, we would have actual images. Its first incredible gift would be a cosmic family album, direct multi-wavelength photographs of dozens of Earth-sized worlds. We wouldn't just know they are there, we would see them as distinct points of light. We could track their orbits, measure their rotation rates by observing changes in brightness as continents and oceans turn into view, and even begin to map rudimentary surface features, distinguishing between land masses, water oceans, and ice caps. This would transform these worlds from abstract data points into real, tangible places. But the true revolution lies in spectroscopy. Once LUVOIR has isolated the light from a planet, it would split that light into a spectrum, a rainbow barcode unique to the chemicals present in that planet's atmosphere. By reading this barcode, scientists could determine the atmospheric composition with stunning precision. They would search for key biosignatures, combinations of gases that are difficult to explain through geology alone and strongly suggest biological activity. The most promising combination is oxygen and methane. On Earth, these gases are constantly produced by life and rapidly react with each other, meaning their persistent coexistence in an atmosphere requires a continuous source, like photosynthesis and methanogens. Finding this pair on another world would be the most compelling evidence imaginable that life exists elsewhere. LUVOIR's capabilities extend far beyond the hunt for alien life. Its powerful vision in ultraviolet, optical, and infrared light would make it a transformative tool for all of astronomy. It could observe the first galaxies forming at the very edge of time with unprecedented clarity, watch stars and planets being born in dusty nebulae in incredible detail, and study objects within our own solar system with a resolution that would make current probes seem rudimentary. It would be a singular engine of discovery for the entire field. The path to launching such a behemoth is long and fraught with technical and budgetary challenges, requiring new heavy-lift rockets and advancements in space assembly. Yet the potential reward is nothing less than a new understanding of our place in the cosmos, offering us the first glimpses of other Earths and perhaps the first definitive proof that we are not the only ones living under the light of a star. Yet as LUVOIR represents a visionary concept for the distant future, a more immediate and focused mission is already taking shape to bridge the gap between our current capabilities and that ultimate goal. The Habitable Worlds Observatory, or HWO, is NASA's next planned flagship astrophysics mission, designed not merely as another telescope, but as humanity's first dedicated planet hunter for life. It takes the most crucial technologies from its predecessors, the infrared prowess of the James Webb Space Telescope and the wide-field survey power of the Nancy Grace Roman Space Telescope, and combines them with a singular, profound purpose: to directly image and analyze the atmospheres of at least 25 Earth-like planets orbiting within the habitable zones of Sun-like stars. This isn't about finding more planets, it's about finding the right ones and determining if any are truly like our own. The core technological challenge HWO must overcome is one of almost unimaginable contrast. Spotting a pale blue dot next to its star has been compared to discerning a firefly silhouetted against a spotlight from 1,000 miles away. To achieve this, the observatory will require a stable, massive mirror and a coronagraph of unprecedented sophistication. Current plans call for a mirror at least 6 meters across, potentially built using segments like webs, but with a surface polished to an even more exacting perfection to minimize scattered light. The coronagraph, an internal instrument that blocks the starlight, will need to be hundreds of times more capable than any previous technology, suppressing the star's glare by a factor of 10 billion to allow the faint whisper of planetary light to finally be seen. This represents a monumental leap in optical engineering, turning a theoretical dream into a practical observational tool. Once the blinding starlight is suppressed, the real science begins. HWO's primary instrument will be a powerful spectrometer. It won't just take pictures of these distant worlds, it will capture their light and split it into a spectrum, a unique chemical barcode. By reading this barcode, scientists can decipher the composition of the planet's atmosphere. They will search for key biosignatures, which are not single gases but combinations of chemicals that are difficult to maintain without a biological source. The most promising combination is oxygen and methane. On Earth, these gases are constantly produced by life and rapidly destroy each other through chemical reactions. Their persistent, simultaneous presence in an atmosphere is a powerful indicator of ongoing biological activity, a signal that something is actively, continually replenishing them. However, the observatory's work is far more nuanced than simply hunting for oxygen. It will perform a holistic environmental assessment of each world. It will look for the presence of water vapor, confirming the world has an ocean. It will measure the abundance of carbon dioxide, which helps regulate planetary temperature and is a key component of a life-sustaining carbon cycle. It will also search for gases like nitrous oxide or chloromethane, which could be produced by different types of microbial life. Crucially, HWO will also be on the lookout for technosignatures, such as unusual concentrations of industrial pollutants like nitrogen dioxide or chlorofluorocarbons, which could indicate the presence of an advanced civilization. This comprehensive analysis will allow us to move beyond simply finding a planet in the habitable zone to definitively characterizing it as a lived-in world or not. The strategic placement of this observatory is key to its success. Like the James Webb Space Telescope, it will likely operate from the Sun-Earth Lagrange Point 2, a gravitationally stable point a million miles from Earth. This location offers a pristine, ultra-stable thermal and orbital environment, free from the distorting effects of Earth's atmosphere and the heat and light reflected by our planet. This stability is non-negotiable. The measurements HWO will make are so precise that even the slightest vibration or thermal drift could ruin the data. It must hold its gaze steady on a single star system for weeks or even months at a time to collect enough photons from its target planet to build a reliable spectrum. This requires a level of pointing stability that pushes the boundaries of current engineering. The ultimate promise of the Habitable Worlds Observatory is to provide a statistical answer to the question of life's prevalence in the universe. By surveying a significant number of Sun-like stars and their terrestrial planets, HWO won't just give us a handful of candidate worlds, it will give us a percentage. It will tell us what fraction of Earth-like planets orbiting Sun-like stars actually develop Earth-like atmospheres suggestive of a biosphere. The answer could range from a profoundly lonely 1% to an incredibly promising 50% or more. Either result would be revolutionary. Finding that we are seemingly alone would force us to confront the incredible rarity and preciousness of our own world. Finding that life-bearing worlds are common would fundamentally reshape our understanding of biology and our place in the cosmos, providing tangible targets for future generations of telescopes and perhaps one day interstellar probes. HWO is designed to be the mission that ends the speculation and begins the era of genuine astrobiological discovery, turning points of light into worlds with stories and just maybe inhabitants. But perhaps the most audacious vision for humanity's future doesn't belong to any government agency, but to a private company with its sights set on a goal of almost unimaginable scale. While NASA and others plan for scientific outposts, SpaceX, under the leadership of Elon Musk, is pursuing something far grander: the establishment of a self-sustaining city on Mars. This is not about planting a flag or conducting short-term research. It is a fundamental, long-term project to make humanity a multi-planetary species. The driving philosophy behind this endeavor is existential risk mitigation, the idea that by establishing a backup civilization on another world, we can ensure the long-term survival of human consciousness in the event of a planetary-scale disaster on Earth, be it a natural asteroid impact, a supervolcano, or a self-inflicted catastrophe. The entire architecture of this vision hinges on a single, revolutionary piece of technology, the Starship system. This isn't merely a rocket, it's the foundational vehicle designed from the ground up for interplanetary colonization. Its fully reusable design is the key to economic viability. Musk envisions not 1 or 2 missions, but a fleet of starships, each capable of transporting over 100 people or more than 100 tons of cargo to Mars. These spacecraft would launch during every favorable orbital alignment window, which occurs approximately every 26 months when Earth and Mars are closest. The initial waves would be primarily robotic, carrying autonomous construction equipment, power generators, life support modules, and the essential infrastructure needed to support human life upon arrival. This preparatory work is critical to ensure that when the first pioneers land, they won't just be surviving in a tin can. They will be stepping into the beginnings of a functioning settlement. The most ingenious and critical element of the entire plan is in situ resource utilization, or ISRU. The sheer cost of launching all the fuel needed for a return trip to Earth from Earth would be prohibitive. The solution is to manufacture fuel on Mars itself. The Starship is designed to run on liquid methane and liquid oxygen, a propellant combination chosen specifically because the ingredients can be sourced from the Martian environment. The process would involve using solar or nuclear power to split Martian water ice, harvested from the poles or subsurface deposits, into hydrogen and oxygen. The hydrogen would then be combined with carbon dioxide, which makes up 95% of the Martian atmosphere, in a chemical process called the Sabatier reaction to create methane and water. This approach creates a closed loop. The water is recycled and the methane and oxygen become rocket propellant. This ability to refuel on Mars transforms the Starship from a one-way lander into a reusable shuttle between planets, fundamentally changing the economics and logistics of colonization. Building a city from scratch on a frigid, radiation-bathed world with a thin carbon dioxide atmosphere is a challenge of epic proportions. The initial habitats would likely be inflatable modules or structures built from Starship hulls themselves, buried under several meters of Martian regolith to provide shielding from cosmic and solar radiation. Over time, more permanent structures would be constructed, possibly using 3D printing technologies that sinter the iron-rich Martian soil into building blocks. A sustainable colony would need to master closed-loop life support, recycling all air and water with near-total efficiency, and develop large-scale agriculture in pressurized greenhouses, using carefully engineered soils and tailored lighting to grow food. The goal is not just sufficiency, but eventual independence, a society that can produce its own food, manufacture its own tools, generate its own power, and manage its own affairs without needing constant resupply from Earth. The societal and ethical dimensions of this project are as complex as the engineering ones. Who gets to go on the first trips? How will a new society, born from scratch millions of miles from Earth, govern itself? What laws and economic systems will it adopt? Musk has often spoken of a spirit of adventure and exploration, attracting pioneers willing to accept high risk for the chance to build something new. The early phases would undoubtedly be extremely dangerous, with colonists facing the very real possibility of death from equipment failure, accident, or the unknown perils of an alien environment. Yet, this very challenge could forge a new chapter in human history, a grand experiment in social organization and resilience. The success of a Martian city would represent the greatest achievement in human exploration, a testament to our ingenuity and a powerful insurance policy for the future of our species, ensuring that the light of consciousness would not be easily extinguished. While the grand visions of SpaceX often dominate the headlines, another titan of industry is pursuing a lunar strategy with a distinctly different, yet equally vital focus. Blue Origin, founded by Jeff Bezos, is channeling its resources into what it sees as the essential first step for a spacefaring civilization, creating a permanent, sustainable infrastructure on the Moon. The cornerstone of this vision is the Blue Moon Mark II lander, a robust and versatile spacecraft designed not just for a single mission, but to become the reliable workhorse for a new lunar economy. This isn't merely about getting there, it's about building the delivery trucks and freight liners that will supply the construction of the first true outpost on another world. The design philosophy behind Blue Moon is rooted in payload capacity and precision. Where earlier landers were constrained by size and weight, Blue Moon is being engineered from the ground up to deliver massive payloads to the lunar surface. The Mark II variant, developed under a NASA contract to serve as the human landing system for the Artemis 5 mission and beyond, is designed to land alongside SpaceX's Starship HLS, offering NASA and international partners a second, complementary path to the Moon. This lander is substantial, capable of ferrying multiple astronauts and tens of tons of cargo, including large prefabricated segments for habitats, power systems, and massive rovers. Imagine it not as a sleek sports car, but as a heavy-duty lunar semi-truck, its cargo bay filled with the very foundations of a base camp. Navigating the treacherous south polar region of the Moon, with its permanently shadowed craters and rugged terrain, requires an extraordinary level of autonomy. Blue Moon employs a sophisticated system called terrain relative navigation. As it makes its final descent, its onboard cameras and computers will compare real-time images of the landing site with highly detailed pre-loaded maps. This allows the lander to identify hazards like large boulders or steep slopes with incredible accuracy and automatically steer itself to the safest possible touchdown point within a targeted area. This technology is crucial for achieving the pinpoint landings necessary to preposition cargo modules and habitats right next to each other, enabling the efficient assembly of a lunar base without requiring astronauts to undertake risky long-distance traverses just to connect power and plumbing between distant landers. A key differentiator for Blue Origin's approach is its choice of propellant, liquid hydrogen. While other landers might use hypergolic fuels or methane, Blue Moon's B7 engine is specifically designed to burn liquid hydrogen and liquid oxygen. This is a strategic decision with profound long-term implications. Water ice locked away in those shadowed polar craters can be split through electrolysis into its constituent parts, hydrogen and oxygen. This means that in the future, Blue Moon could potentially be refueled using propellant mined and processed on the Moon itself. This turns the lander from a single-use vehicle into a reusable shuttle that could run between the lunar gateway and the lunar surface, drastically reducing the long-term cost of sustaining a presence on the Moon. It embodies the principle of using local resources, a concept that is absolutely essential for any lasting expansion into the solar system. Beyond its powerful engine, the lander incorporates advanced hydrogen fuel cell technology to provide power during the long lunar night, which lasts about 14 Earth days. Solar power is abundant during the lunar day, but surviving the frigid, sunless night is one of the greatest challenges for any prolonged operation. Fuel cells, which generate electricity by combining hydrogen and oxygen, offering a far more efficient and long-lasting energy solution than batteries alone. This capability ensures that astronauts and their critical systems have a reliable power source for extended surface operations, allowing for scientific research and base maintenance to continue uninterrupted through the darkness. Blue Origin's broader vision, often referred to as the Blue Alchemist Program, extends far beyond the lander itself. The company is developing the technology to make solar cells and transmission cables using only lunar regolith, the dusty soil that covers the Moon's surface. This vision of a self-sustaining loop using local water ice for propellant and local materials for construction and power positions Blue Moon not as a standalone vehicle, but as the central delivery mechanism for an entire lunar industrial revolution. It represents a methodical, infrastructure-first approach to space exploration, focusing on creating the logistical backbone that will allow humanity to not just visit the Moon, but to truly stay. In this partnership of giants, if Starship is the daring interplanetary freighter, Blue Moon is the indispensable local utility vehicle, ensuring that when we arrive, we have the tools, the power, and the supplies to build a future. But while rockets rely on the violent expulsion of mass to generate thrust, there exists a far more elegant and ancient method of crossing the void, one that requires no fuel at all, only the gentle, constant pressure of sunlight itself. For centuries, science fiction writers have dreamed of sailing the solar winds, and now that dream is becoming a reality with a new class of mission that turns light into motion. Solar sail technology represents a fundamental shift in how we think about propulsion, trading the explosive power of chemical rockets for the patient, infinite push of photons. This isn't just a new engine, it's a new paradigm for exploration, one that unlocks mission profiles impossible for any conventional spacecraft. The principle behind a solar sail is beautifully simple, grounded in a truth discovered by James Clerk Maxwell over a century ago. Light, despite having no mass, carries momentum. When photons from the sun strike a surface, they impart a tiny, tiny bit of that momentum to it. For everyday objects, this push is utterly insignificant, completely overwhelmed by gravity and friction. But in the perfect vacuum of space, where there is nothing to slow you down, and if you have a surface large enough and lightweight enough to capture a meaningful number of photons, that tiny push becomes a continuous, cumulative acceleration. It's the ultimate tortoise and hare scenario. While a chemical rocket burns all its fuel in a matter of minutes for a brief, powerful burst of speed, a solar sail pushes gently, hour after hour, day after day, week after week, slowly building up velocities that could eventually surpass those of any conventional craft. Transforming this elegant theory into a working spacecraft is a monumental feat of materials science and engineering. The challenge is to create a sail that is incredibly vast yet nearly weightless, strong enough to withstand the rigors of deployment and the tension of maneuvering, and reflective enough to maximize the photon push. Modern sails are constructed from polymers like polyamide that are thinner than a human hair and often coated with a thin layer of aluminum to enhance reflectivity. The real magic lies in the deployment. These vast sheets, sometimes spanning thousands of square feet, must be folded into a payload no larger than a shoebox and then unfurled in zero gravity with perfect precision, using a system of lightweight booms that slowly uncoil like tape measures to stretch the sail taut. A single snag or tear could be mission-ending, making this one of the most delicate and daring maneuvers in all of spaceflight. One of the most compelling near-term applications for this technology is demonstrated by the Near-Earth Asteroid Scout, or NEA Scout. This small spacecraft, deployed from the Artemis 1 mission, was designed to use its solar sail to slowly and methodically journey to a small asteroid, maneuvering itself into a close proximity orbit for detailed study. Its mission profile showcases the solar sail's greatest strength, infinite patience and precision. A conventional mission to such a target would require a complex series of fuel-burning orbital maneuvers, but NEA Scout could adjust its trajectory subtly and continuously, using its sail to literally tack against the solar radiation pressure, much like a sailboat tacks against the wind. This allows for incredibly fine-tuned approaches to small, low-gravity objects that would be dangerously difficult to reach with traditional thrusters. Looking further ahead, more ambitious sail concepts promise to open entirely new windows into our solar system. The proposed solar cruiser mission was designed to use a sail of truly enormous scale, over 17,000 square feet, to achieve a unique and vital orbital position. It aimed to use the constant photon pressure to hover in a stable position that is not in a natural orbit, allowing for continuous, uninterrupted observation of the Sun's polar regions. Understanding solar activity at the poles is critical for improving our models of the Sun's 11-year cycle and for predicting the solar storms that can threaten satellites and power grids on Earth. This kind of station keeping is incredibly fuel-intensive with conventional propulsion, but for a solar sail, it's a natural and fuel-free state of being. Perhaps the most thrilling future application lies in the potential for interstellar travel. While a solar sail accelerates slowly within the inner solar system, that acceleration is constant. A powerful ground-based laser array could theoretically beam additional energy to a sail, accelerating it to a significant fraction of the speed of light. Such a craft, a true star sail, could reach the nearest stars in a matter of decades rather than millennia. While this remains a long-term vision, smaller-scale versions could be perfect for rapid response missions to intercept the next interstellar object that passes through our solar system, like Oumuamua. A solar sail could be pre-positioned and then launched at a moment's notice, using the sun's own energy to chase down and rendezvous with a visitor from another star system, giving us our first real chance to examine such an object up close. The true revolution of solar sailing is one of sustainability and longevity. A conventional mission ends when its last drop of hydrazine monopropellant is exhausted, its fate sealed. A solar sail, barring mechanical failure or a collision, has no such expiration date. It can continue to accelerate, decelerate, and maneuver for years, even decades, limited only by the longevity of its instruments and the resilience of its material against the relentless bombardment of micrometeoroids and ultraviolet radiation. This turns a spacecraft from a disposable vehicle into a persistent, adaptable presence in space, capable of undertaking multi-target tours of asteroids or maintaining its vigil over the sun for a full solar cycle. It proves that sometimes the most powerful way to explore the universe is not to fight against its forces, but to harness them with a gentle, silent, and infinitely patient touch. Yet for all the promise of solar sailing within our own solar system, one visionary project aims to harness this ancient starlight in a way that is almost beyond belief, seeking to accomplish nothing less than the first interstellar voyage. Breakthrough Starship is not a mission in the traditional sense. It is a breathtakingly ambitious research and engineering program, a moon shot in the most literal meaning of the phrase. Its objective sounds like it's lifted from the pages of the most optimistic science fiction, to send a fleet of tiny, gram-scale spacecraft to our nearest stellar neighbor, the Alpha Centauri system, at 20% the speed of light. At that staggering velocity, the journey of 4.37 light-years would take just over 20 years, with another 4+ years for the data to travel back to us. Within a single human lifetime, we could receive our first postcards from another star. The core technology behind this audacious concept is a radical scaling up of the solar sail principle, but with a crucial and powerful twist. Instead of relying on the gentle, diffuse pressure of photons from our sun, Starship proposes building an enormous ground-based array of lasers, a phased array stretching for potentially kilometers. This light beamer would focus all its energy onto a single, ultra-thin, and highly reflective light sail attached to one of the tiny probes called a Starship. For a few minutes, this sail would be bathed in a concentration of light 1,000,000 times more intense than sunshine, experiencing an acceleration force thousands of times greater than gravity. This is the key, the ability to achieve phenomenal acceleration over a very short period, rocketing the nanocraft to their target velocity in mere minutes before they coast for the decades-long journey across the interstellar void. The engineering challenges involved are so profound they border on the fantastical, requiring breakthroughs across half a dozen fields of physics and material science. The light sail itself must be perhaps only a few hundred atoms thick, yet strong enough to withstand an instantaneous energy delivery equivalent to a nuclear blast without vaporizing or tearing apart. It must also be phenomenally reflective, around 99.999%, to avoid absorbing the laser energy that would instantly incinerate it. Meanwhile, the laser array required would need to be the most powerful and precisely coordinated energy projector ever built. a system with a combined power output greater than that of an entire nation, all focused on a spot the size of a sailing vessel hundreds of thousands of miles away, and it must maintain that focus perfectly through Earth's turbulent atmosphere. Then there is the Starship, the payload. This is where the revolution in miniaturization comes into play. The entire functional spacecraft, its cameras, photon thrusters for minute course corrections, power supply, navigation equipment, and communication laser, must be shrunk down to the size of a postage stamp and weigh no more than a gram. This necessitates a level of nanotechnology that does not yet exist, integrating components like miniature cameras smaller than a grain of salt and atom-scale sensors. Perhaps the most daunting challenge of all is communication. How does a 1-gram probe light years away, powered by a tiny nuclear battery or a minuscule laser-charged capacitor, send a signal strong enough to be detected back on Earth? The solution would likely involve using the light sail itself as an antenna, focusing an incredibly weak laser beam that our most sensitive telescopes would have to struggle to detect from across the interstellar gulf. Despite these monumental hurdles, the potential scientific return is so transformative that it justifies the high-risk, high-reward approach. The primary target is Proxima Centauri b, an Earth-mass exoplanet orbiting within the habitable zone of the red dwarf star Proxima Centauri, which is part of the Alpha Centauri triple-star system. Our current telescopes can only infer this world's existence through indirect methods. A starshot flyby, even at a significant fraction of light speed, could capture direct images. Imagine a grainy, pixelated photograph not of a blurry dot, but of a distinct crescent shape, revealing continents and oceans on a world 4.37 light-years away. The mere act of distinguishing between a solid surface and a gaseous one would be a monumental achievement. Simple spectrographic analysis from the flyby could determine the composition of its atmosphere, searching for the telltale signs of water vapor, oxygen, or methane, and answering the ultimate question of whether this nearest world could harbor life. The philosophy of Breakthrough Starshot embraces a paradigm shift in exploration. Instead of building one colossal, fragile, and prohibitively expensive generation ship for a millennia-long journey, send thousands of tiny, cheap, and redundant probes. The plan calls for a swarm, not a single vessel. This acknowledges the extreme peril of the journey. Collisions with interstellar dust grains, which at 20% light speed would hit with the energy of a particle accelerator beam, could easily destroy any one craft. But by launching a vast fleet, the mission ensures that even if 99.9% of the probes fail, a handful could still make it through, their data combining to give us a complete picture of the Alpha Centauri system. This approach transforms interstellar travel from a single, all-or-nothing gamble into a statistically viable endeavor. While the goal is a flyby of another star, the technological spin-offs from pursuing Starshot could revolutionize science and industry here on Earth. The advanced photonics and laser technologies developed for the light beamer could lead to new forms of clean energy transmission and powerful new scientific instruments. The breakthroughs in extreme miniaturization required for the starships would cascade through computing, medicine, and robotics. The advanced communication systems could redefine deep space networking. In striving for this ultimate goal, we would inevitably develop a suite of transformative technologies that would reshape our world long before the first probe ever reached Alpha Centauri, proving that the value of such an audacious dream lies not only in the destination but in the incredible journey of discovery it forces us to undertake. Imagine a future where ailing satellites don't become eternal monuments to our technological limitations, but instead get a new lease on life from a robotic mechanic making a house call in the void. This is the transformative promise of on-orbit servicing, a field poised to fundamentally change our relationship with space from one of disposable abandonment to one of maintenance and upgrade. For decades, the design of every spacecraft has been shackled by a cruel reality. Once launched, it is utterly alone. Every component must be over-engineered for maximum longevity, every drop of fuel meticulously rationed, and any failure, no matter how minor, is often a mission-ending catastrophe. This paradigm has left a graveyard of brilliant but dead machines in its wake and placed a hard limit on our ambitions. But now, NASA is pioneering a new approach with missions like Awesome One, which stands for on-orbit servicing, assembly, and manufacturing, demonstrating that we can finally extend a helping hand to our robotic emissaries. The Awesome One mission is a technological showcase, a floating testbed for a suite of capabilities that read like science fiction. Its primary task is a daring and precise ballet in microgravity, to rendezvous with an aging, unprepared satellite not designed to be serviced, the Earth-observing Landsat 7, and gently refuel it. This alone is a monumental challenge. It requires a robotic arm to meticulously snip through layers of protective insulation and unscrew a complex fill and drain valve, all while exerting just the right amount of force to avoid sending the client satellite into an uncontrolled spin. Success would prove that even our legacy space infrastructure can be given more time, saving billions of dollars and delaying the creation of more debris. But Awesome One's ambitions extend far beyond refueling. The mission will also demonstrate in space manufacturing by using a second, smaller robotic arm to assemble a communications antenna from a kit of parts, building a structure that could never have fit inside a rocket fairing during launch. This opens the door to constructing massive telescopes and antennas in orbit, unconstrained by the size limits of a launch vehicle. The implications of mastering these skills ripple across every aspect of space operations. The most immediate benefit is the drastic reduction of space debris. A significant portion of the thousands of derelict objects cluttering Earth's orbits are satellites that ran out of station keeping fuel or suffered a simple, fixable malfunction. With a servicing capability, these satellites could be refueled, repaired, or, if beyond saving, deorbited in a controlled manner by a servicer spacecraft, actively cleaning up the environment. This changes the entire economic calculus of satellite design. Instead of building a spacecraft to survive untouched for 15 years at immense cost, companies could build for a shorter initial lifespan with the understanding that cheaper, modular upgrades and refueling missions are part of the long-term plan. This could democratize access to space, allowing for more frequent iterations of technology and reducing the massive financial risk of a single launch. Perhaps the most exciting prospect is for the future of space-based observatories. The Hubble Space Telescope stands as the ultimate testament to the power of servicing. Initially launched with a flawed mirror, it was 5 subsequent shuttle missions that repaired its vision, upgraded its instruments, and replaced its failing components, ultimately enabling its 30-plus years of revolutionary discovery. Hubble is the exception that proves the rule, requiring a colossal and expensive human effort. Awesome One and its successors aim to make that capability routine and robotic. Imagine a next-generation telescope, even larger than James Webb, designed from the start with standardized ports, grapple fixtures, and modular components. A robotic servicer could periodically visit to swap out old instrument modules for new ones featuring the latest technology, essentially ensuring the observatory never becomes obsolete. It could top off its fuel to maintain a perfect orbit indefinitely and make repairs we never could have anticipated. This transforms a space telescope from a static instrument into an evolving observatory, capable of growing and adapting alongside our scientific curiosity. This shift towards a service-based infrastructure in space marks a turning point as significant as the transition from sail to steam in maritime history. We are moving from merely launching vessels across the ocean of space towards building a sustained and sustainable presence there, complete with a support network. The technologies proven by missions like Awesome One will form the foundation for assembly of large space stations in lunar orbit, the construction of fuel depots for interplanetary journeys, and the maintenance of critical communications networks that will connect future explorers. It represents a maturation of our capabilities, a move away from the era of one-off, disposable missions and into a new age where space is a domain we don't just visit, but where we work, live, and maintain our tools, building a lasting and continuously improving infrastructure for all of humanity. But to turn a scientific outpost into a true settlement, we need more than just a delivery service. We need to learn how to live off the land. For all our ambitions on the moon, one truth remains inescapable. Launching anything from Earth's deep gravity well is phenomenally expensive. Every gallon of water, every tank of oxygen, every kilogram of rocket fuel sent from home costs a fortune and severely limits our reach. The solution to this logistical nightmare has been hiding in plain sight, or rather in permanent shadow for billions of years. Locked away in the frigid, sunless depths of the lunar polar craters are vast reserves of water ice, a treasure more valuable than any mineral. The race is now on to become the first interplanetary prospectors, to develop the technology that will mine this ice and transform it into the very resources we need to not just visit space, but to thrive there. These are not merely patches of frost. Current data from orbiters like LRO and India's Chandrayaan-1 suggest these deposits could amount to millions of metric tons. The most promising reservoirs are found in craters like Shackleton at the South Pole and Peary near the North Pole, where the sun never rises above the crater's rim. In these eternal abysses, temperatures plummet to -400 degrees Fahrenheit, colder than the surface of Pluto, creating a deep freeze so absolute that water ice can remain stable for eons. This ice isn't a smooth sheet. It's likely mixed with the lunar soil or regolith, requiring sophisticated extraction methods. Unlocking it is the key to a self-sustaining presence, and the benefits form a powerful trifecta crucial for survival. First and most fundamentally, this water means life support. It can be purified for astronauts to drink and used to grow food in hydroponic gardens, but through a process called electrolysis, which uses electricity to split water molecules, it can be broken down into its constituent parts, breathable oxygen for life support and hydrogen. This alone would liberate lunar bases from the exorbitant cost of shipping these vital consumables from Earth, making longer and larger crew rotations feasible. The second major benefit is radiation shielding. Water is an excellent absorber of harmful cosmic radiation. By storing mined water in tanks around habitats or even using bags of water ice as building blocks within habitat walls, we could create a crucial barrier against the constant, dangerous radiation that baths the lunar surface, protecting astronauts from increased cancer risks and other health effects. The third and perhaps most transformative application is the creation of rocket propellant. The same hydrogen and oxygen produced from electrolysis are the exact components used in the most common types of high-efficiency chemical rocket engines. This is the game changer. A lunar outpost that can produce its own fuel effectively becomes a gas station in space. Ships like SpaceX's Starship could launch from Earth with minimal fuel, rendezvous with a lunar fuel depot to top off their tanks, and then embark on journeys to Mars or beyond with a full load. This completely revolutionizes the economics of deep space travel. Instead of launching all the fuel for a round trip from Earth, a tremendously massive and expensive endeavor, we can refuel in lunar orbit using resources gathered locally. The moon transforms from a destination into a vital waypoint, the first port of call on the cosmic coastline. Recognizing this potential, a wave of missions is now being prepared to turn this theory into practice. NASA Artemis Program includes the Polar Resources Ice Mining Experiment, or PRIME-1, which will be one of the first on-the-ground efforts. This payload will land on a ridge near the South Pole that receives near-continuous sunlight adjacent to a permanently shadowed area. It will use a robotic drill to attempt to pull up a sample of ice-rich regolith, and then demonstrate a basic heating element to extract the water vapor, proving the core extraction concept. Following close behind, NASA Volatile's Investigating Polar Exploration Rover, or VIPER, will play the role of a robotic prospector. This mobile rover will traverse into the shadowed regions, using a drill to take samples from various depths and locations, creating the first detailed maps of the distribution and concentration of lunar water ice. This data is absolutely critical for future miners. It will tell them exactly where to set up shop for the highest yield. They will not be alone. Private companies are also charging into this new frontier. Astrobotic, under a NASA contract, is developing its own ice drilling payloads for future lander missions. Meanwhile, the Japanese space agency JWST is collaborating with Toyota on a pressurized, autonomous rover that could support long-duration prospecting and resource mapping missions. The ultimate goal for many of these entities is to demonstrate not just extraction but the full cycle, mining the ice, purifying the water, storing it, and then using electrolysis to split it into oxygen and hydrogen, liquefying those gases, and finally storing them as supercooled propellant. Each of these steps presents immense engineering challenges in the Moon's harsh environment, with its abrasive dust, extreme temperature swings, and low gravity. The successful development of a lunar water economy would mark a paradigm shift as significant as the advent of seafaring or transcontinental flight. It moves humanity from being mere visitors in space to becoming residents. It promises a future where the Moon is not a dead end but a springboard, a hub for construction, science, and a launch pad for the rest of the solar system. The machines that will first crack the icy soil of those dark craters are doing more than just mining. They are laying the foundation for the first true branch of human civilization beyond our home planet. Now, let us turn our attention from the resources of other worlds to a revolutionary idea for solving the energy challenges on our own, an idea that sounds like pure science fiction, but is edging closer to reality with each passing year. Imagine a power source that never fades with the setting sun, never falters on a cloudy day, and operates 24 hours a day, 365 days a year. This is the promise of space-based solar power, a concept that envisions vast constellations of satellites in Earth orbit, soaking up the unfiltered, intense energy of the sun and beaming it down to receiving stations on the surface. Up next, we have a mission that isn't about exploring a distant planet, but about fundamentally reshaping our own world's energy infrastructure. The core principle is brilliantly simple. In space, beyond the filtering and diffusing effects of our atmosphere, sunlight is far more potent and, crucially, always available. A solar panel in geostationary orbit receives up to 10 times more energy than one on the ground and is never interrupted by night. The challenge, of course, has always been how to get that energy back to Earth. The proposed solution is wireless power transmission. The collected solar energy would be converted into either a low-intensity microwave beam or a focused laser beam. Think of it not as a destructive ray, but more like a highly targeted wireless charger, but on a global scale. This beam will be precisely aimed at a dedicated receiving station on the Earth's surface, called a retina, which is a vast field of simple wire mesh that converts the microwave energy back into electricity to be fed directly into the power grid. The potential benefits of perfecting this technology are nothing short of transformative for global energy and climate security. Unlike terrestrial solar and wind farms, which are intermittent and require massive investments in energy storage solutions like batteries, a space-based system provides baseload power constant, reliable, and predictable. A single, large-scale solar power satellite could generate multiple gigawatts of power, enough to rival a nuclear power plant, but without any radioactive waste or fuel requirements. A network of such satellites could provide a substantial portion of the world's electricity needs, drastically reducing our reliance on fossil fuels and becoming a central pillar in the fight against climate change. Furthermore, this power could be beamed to virtually any location on the globe, offering a powerful tool for energy independence and for bringing clean, reliable electricity to remote or disaster-stricken areas that are currently off the grid. The path from concept to reality is being paved by a new wave of demonstrator missions from nations and private companies eager to prove the core technologies. The California Institute of Technology has already had remarkable success with its Space Solar Power Demonstrator project, which included a successful test of transferring power from a prototype in space to a receiver on Earth. Meanwhile, the Japan Aerospace Exploration Agency, JWST, has been a long-time leader in this field and is planning a major milestone demonstration in the coming years, aiming to beam power from orbit to the ground. Similarly, the European Space Agency has proposed its ambitious Solaris program, a detailed feasibility study to lay the groundwork for a potential future operational system. Even the United Kingdom is investing in its own project to develop the underlying technology. Each of these projects is tackling the immense engineering hurdles that have kept this idea on the drawing board for decades. They are developing the ultra-lightweight, highly efficient photovoltaic cells needed to make the massive solar arrays economically feasible to launch. They are perfecting the precision pointing and control systems required to keep a tight energy beam locked onto a rectenna from over 36,000 kilometers away, even through the upper atmosphere. They are conducting rigorous safety studies to ensure the low-intensity microwave beams pose no risk to aviation, wildlife, or human health, with the beam only activating when it has a confirmed lock on its designated receiver. These demonstrators are the crucial first steps, the small-scale proofs of concept that will de-risk the technology and convince governments and investors to fund the full-scale versions. Successfully deploying a functional space-based solar power network would represent one of the most ambitious infrastructure projects in human history, but the payoff would be a permanent solution to clean energy. It would create an entirely new economic sector in space, driving down the cost of access through massive demand for launch services and in-space manufacturing. It would provide a stable, abundant source of energy that could power carbon capture technologies, synthesize green hydrogen fuels, and support a growing global population without further damaging the planet. This mission goes beyond mere exploration. It is about using our presence in space to directly and profoundly nurture and protect life on Earth, turning the boundless energy of the sun into an endless, clean river of power for all humanity. For centuries, the most effective way to find a world beyond our solar system was to wait for it to cross in front of its star, causing a telltale, periodic dip in brightness. This transit method has been wildly successful, revealing thousands of exoplanets. But as we push toward the ultimate goal, finding a true Earth twin around a sun-like star, this technique hits a formidable wall. The signal of an Earth-sized planet transiting a sun-like star is breathtakingly faint, a dip in starlight of just 84 parts per million. And to confirm its orbit within the habitable zone, you need to witness that tiny blink not just once, but multiple times over the course of a year or more. To climb this mountain of precision, we need an observatory of unprecedented stability and photometric accuracy. This is the monumental challenge that the European Space Agency's Pluto mission is designed to meet. Pluto, which stands for planetary transits and oscillations of stars, is a marvel of optical engineering built around a simple but powerful concept: more eyes are better than one. Unlike most space telescopes that feature a single large mirror, Pluto design is radically different. It carries an array of 26 individual cameras, all working in perfect synchrony. 24 of these are normal cameras, each with a large field of view, which work together to perform the mission's core task. They will stare unblinkingly at vast patches of the sky for years at a time, monitoring the brightness of up to 1 million of the brightest stars. This multi-camera approach provides incredible redundancy and, more importantly, a massive boost in measurement precision. By combining the data from all these eyes, Pluto can average out noise and achieve the stellar photometric stability needed to detect those whispers of other Earths. The remaining 2 cameras are fast cameras, designed to observe a smaller subset of the very brightest stars at an even higher cadence, pushing the boundaries of what's possible. This relentless, ultra-precise monitoring serves 2 profound and equally important scientific goals. The first and most headline-grabbing is the hunt for planets. Pluto is specifically targeting Sun-like stars, those of spectral types G and K, which are the most similar to our own. Its extended observing campaigns, lasting 2 to 4 years each, are long enough to detect multiple transits of planets orbiting within the habitable zone, the region around a star where temperatures could allow liquid water to exist on a rocky surface. But Pluto is far more than a simple planet finder. It is a complete planetary system characterizer. By measuring the precise timing of transits and the tiny deviations caused by gravitational tugs from other planets in the same system, it will allow scientists to determine the masses and orbits of all the worlds in that system with incredible accuracy. For the first time, we will not just find individual planets. We will build a complete census of entire planetary architectures around stars like our Sun, revealing whether our own solar system's layout is common, rare, or entirely unique. The mission's second objective is perhaps less intuitive but no less critical. It will listen to the music of the spheres. This is where the oscillations in its name comes from. Stars are not silent, static balls of gas. They resonate like giant musical instruments, pulsating with sound waves that travel through their interiors. These vibrations cause tiny, rhythmic fluctuations in the star's brightness and temperature. Pluto's exquisite sensitivity is perfectly tuned to detect these oscillations, a field of study known as asteroseismology. By analyzing this stellar song, scientists can perform a detailed ultrasound on each star. The frequencies of these oscillations reveal the star's internal structure, its density, temperature, composition, and even its very precise age. This is the master key that unlocks the true nature of any planets found orbiting it. Think of it this way. If you find a planet transiting a star, you can measure the planet's size relative to the star. But to know the planet's true size, you must know the star's exact size with incredible precision. Asteroseismology provides that. If you want to know the planet's true orbital distance to see if it's truly in the habitable zone, you need to know the star's mass and temperature with extreme accuracy. Asteroseismology provides that too. And if you want to know how old the planetary system is, whether life has had billions of years to evolve or just a brief moment, asteroseismology can date the star to within a stunning 10% accuracy. Pluto doesn't just find the planets, it performs a full background check on their parent stars, ensuring we are not fooled by imposters and that every measurement of a new world is rock solid. The ultimate treasure from this mission will be a curated catalogue of the best and brightest Earth-like worlds orbiting Sun-like stars. These will not be faint, distant specks around dim red dwarfs, but planets around stars similar to our own, whose light is bright enough for the next generation of telescopes to analyze. Pluto will hand the astronomical community a list of prime targets, telling them exactly where to point behemoths like the James Webb Space Telescope and the Future Habitable Worlds Observatory. For these giant observatories, time is their most precious resource. Pluto will tell them precisely which stars are worth spending hundreds of hours of observation time on to perform atmospheric spectroscopy, sniffing the air of these new worlds for signs of water vapor, oxygen, methane, and other potential biosignatures. It is the essential scout, the cosmic cartographer, identifying the most promising islands in the vast ocean of space for future explorers to investigate in detail. By providing the precise characteristics of both the planet and its star, Pluto will lay the essential groundwork for the day we might finally answer the question of whether we are alone, having first shown us exactly where to look. What we've witnessed across these 25 missions is far more than a simple list of spacecraft and destinations. This is a symphony of human ambition, a coordinated effort across decades and disciplines that together forms the most comprehensive plan for our future in space ever conceived. We are no longer merely sending probes to take pictures. We are building the foundational infrastructure for a multiplanetary civilization. We are deploying sentinels to guard our world, time machines to peer into the past, and oceanographers for alien seas. Each mission, from the lunar gateway to the interstellar dream of Starship, represents a critical piece of a sprawling puzzle. When assembled, this puzzle reveals a new portrait of humanity, not as a species confined to a single world, but as one taking its first conscious, determined steps into a cosmic ocean. These ventures address the most profound challenges and questions we face. They seek to protect our planetary home by finding and tracking asteroids that could threaten our very existence. They strive to solve the universe's deepest mysteries, the nature of dark energy, the origin of the first galaxies, and the violent processes that forge the planets. And perhaps most compellingly, they are on the cusp of answering a question that has echoed through human history: are we alone? By probing the subsurface oceans of Europa, sniffing the atmospheres of exoplanets, and analyzing the chemical factories on Titan, we are not just looking for water or interesting chemistry. We are actively hunting for the signatures of life itself. A single positive result from any one of these missions would irrevocably change our understanding of biology and our place in the cosmos. This is not a future reserved for scientists and astronauts in distant decades. The timeline for these discoveries is unfolding right now in our lifetime. The James Webb Space Telescope is already rewriting textbooks. The Artemis Program aims to return humans to the moon before the end of this decade. Missions like Dragonfly and the Mars Sample Return are scheduled to reveal their secrets in the 2030s. You have a front row seat to the greatest era of exploration in human history. We encourage you to follow along, watch the launches, marvel at the new images, and share in the wonder of each new discovery. These are your missions, the endeavors of a species awakening to its potential, funded by public support and driven by a shared, innate curiosity. So, as we look up at the night sky, let it be with a new sense of anticipation and ownership. Each pinprick of light is no longer just a star, it is a potential sun for another Earth. The moon is not just a distant beacon, but our next doorstep. Mars is not a red dot, but a future frontier. These 25 missions are our collective commitment to turning that vision into reality. They are the tangible expression of a promise to ensure that humanity's story continues, that our curiosity endures, and that one day we will truly call the stars our home. The greatest chapters are yet to be written, and